year, I've done a lot of derivations. I don't want to do another one. But I want to show you where this comes from. You don't need to copy this down. I do want to relate it back to something you do know. Okay? Because we're going to be using a new formula. And I'm not going to derive the formula for you. I'm not even going to derive the constant. But I want to show you where it comes from and why it all makes sense. And then we're going to do some problems with it. All right? And let's talk about physics first. You guys all know from physics. Oops, I never did my other one. You guys all know from physics something about work. Who could tell me something about work? What's the formula for work? Yeah, everybody probably knows that. And this is from Physics 1. This isn't like EM. This is just, work equals force times distance. You probably saw it one of the first equations you got, I'll bet you, in physics, right? It was Physics 1. Even if you guys are only in Physics 1 this year, you've seen that equation at least, okay? All right, well, that's nice. So, how does that relate to what we're doing now with pressures and volumes and temperatures and basically the ideal gas law, which we just kind of tried to hook into here? That's what I want to get to. Chemistry says this. You may remember this actually from, I just mentioned it briefly in the thermodynamics chapter. We talked about work. How, remember when we talked about work? I said most of the work that's done by chemical reactions is done not by moving a car across a track with no resistance and calculating the momentum and stuff like that. That's what Mr. Schrader talked about. Most of our work is done by pressure and volume changes. Okay? If I push down on this, I'm doing work on the system. If I had a reaction in here that gave off a gas, it would create pressure and move this syringe up, the plunger up. And it would do work, okay? So, I've done work by the system. So, I just mentioned that very briefly back then, and we talked a little bit about it. So in chemistry, it's not about a force moving through a distance necessarily, like a car or, whatever, billiard ball or whatever, doing work that way. It's more about pressure times volume, a pressure and a volume. And I wanted to show you how the two things are the same. That's the crazy part here. How is pressure times volume the same as a force times a distance? Because I bet you most of you can't see that. All right, but it really is. Let's think about it. What, after all, is pressure? Pressure is a force. If you looked at, in fact, I'm going to do it today. Remember my little animation I had with the balls that were all around, moving really fast and hitting the sides of the container? I'm going to do that demo today. I'm going to do this demo today. Remember when I filled this with water, I put a paper over the top, I turned it upside down? That's actually for Chem 1 today. What keeps that water up here is the pressure of the air banging into that paper. I'm not going to do it again for you guys, but if I have a piece of paper over here, that water all stayed up there. That water's heavy. People always tell me, what's keeping that in there? Water pressure. No. Water pressure does not want this water to stay in here. Gravity. Gravity wants that water to go out. What's keeping that water in there when I have a piece of paper like this is the air pressure. The air banging into the surface of that piece of paper. And I'm going to do that for Chem 1 today. So basically, pressure is a force per unit area. I push on this plunger. The area of that plunger, that disc, pushing down. Okay, so the force being pushed on an area. That's what pressure is. Volume is a length cubed, or distance cubed. Think about it, right? If I had a cube, all right, length times width times height, that would be the. So this is why it all works. I'm going to get to a very familiar equation and a very familiar unit for you in a second. Okay? Work will be force per unit area times a distance cubed. What is that? If I multiply that out, what do I have? Force times distance, because the distance squared and distance cubed, a volume is a distance cubed. A pressure is a force over a square, an area, which is a square distance, right? So if you multiply it out, you get force times distance. That's basically all you get. You get signed in?
Yeah.
All right? So,
You only got one.
and here's your familiar unit, basically. Would you all not agree that work is measured in Newton meters?
No.
You guys have all done work, and you've all measured it in Newton meters, right? Now, again, you're not copying any of this down. All right, this is for those of you who just walked in. I'm just going over where I'm going with this. I'm going somewhere with this, believe it or not. I wouldn't be doing this for no reason. That's all I wanted to do. I actually have to use a whole different constant. here for my ideal gas law, which you're going to say, where did that come from? Well, I first wanted to go over why I could substitute in pressure times volume wherever I have work. Okay, work can be substituted in for either way. Work can be in for that, or pressure volume can be in for work. They're the same thing. And again, the point is, basically, I'm taking my Newton meters, which is my Newton meters squared, which is my pressure, times my meters cubed, which is a volume, and I will get Newton meters, which is your physics definition of work, or what's another name for a Newton meter? A joule, exactly. Joules are joules. Okay? So all joules equals joules. So that's what my whole point is. Pressure, force times distance, your physics definition of work, is the same as pressure times volume, your chemistry definition of work. Now, why did I say all that? Well, here's why. Let's get back to our ideal gas law, PV equals nRT. And again, you're still not copying this. You are going to be copying something in a minute. PV equals nRT, and I've done this, and I will do this, not today, but actually next week in Chem 1. I'm going to rearrange this. If you look back in your notes, you will find me rearranging this and solving this for R. We used R, right, and we've been using R. We've already used R this year, and we used it all of last year as 0.0821 liter atmospheres per mole Kelvin. It was that crazy unit. We talked about that. It's just a constant related all this stuff together. And you can clearly see why it's liter atmospheres. Liters are volume, pressure is atmospheres, moles is N, and Kelvin is temperature. Now, I'm going to use a completely different R. A number that's just going to come out of nowhere if I weren't doing this. Why am I going to use a totally different R? Because I'm going to try to relate work to my gas law. So where I have PV here right now, where I have pressure and volume, I'm going to substitute in work. Okay? So instead of R equal PV over NT, R is going to equal work over NT. And it works. That's no pun intended. It actually works. All right? And so I can get my answer. I can be solving for a thermodynamic question instead of just an equilibrium problem, because work is measured in joules, as you know, right? And so if I plug all the information in, instead of using liter atmospheres per mole Kelvin, I use joules per mole Kelvin, the number's not 0.0821. Obviously, I'd be using different numbers. The number turns out to be, and you don't have, again, none of this that you have to copy, 8.314 joules per mole Kelvin. That's the same R if I use work instead of pressure and volume separately, okay, if I use joules. And that's why we're going to be using this number. Now, I just wanted to show you where I came from. Now it's time to start copying some of this stuff down, because the reason we're going to use that is we're actually going to put together an old friend with a new one. We have K, which is the equilibrium constant, but you may remember my goal of thermodynamics chapter was delta G, to find out if a reaction was spontaneous or not. Delta G is in joules per mole. All right? That's what delta G measures. All right? I can actually figure out, they're related. K and delta G are related. And that's what I'm going to talk about now. So copy this down. How are delta G and K related? We all know what delta G meant. What did delta G tell us? It told us whether the reaction was spontaneous or not. We spent our entire chapter learning about that. First, we found the delta H, right? The enthalpy of the reaction. Was that positive or negative? Was I going from high to low energy, in which case that's favors spontaneity? Was the entropy becoming greater? And what was the temperature? Those three things, throw them together, we got delta G. Kc, or any of the Ks, are relating equilibrium, where this guy lies. All right? Now, it probably makes sense to you, and it will. It should make sense. That K should be related to delta G in some way, shape, or form. Just because a reaction is reversible doesn't mean I can't predict whether it's going to... if K says... Let's just use a little common sense. Let's say K is very large. What does that tell me? The reaction is going mostly to products, right? Which means it's going to be spontaneous, right? It's going to favor spontaneity. All right? What if K is really, really small? What's that going to tell you? Most of it's staying over here. It's not going to be very spontaneous, you see? So that's how they're related, but I got to put all this together and do the calculations as well and show you the equation. All right? Delta G and delta and K are related by that equation. Negative RTLNK. Now, don't ask me to derive this. I've done a lot of derivations. That equation is on this sheet, which, by the way, who was absent and didn't get one of these sheets? These are the sheets that have all your equations on them. Who was absent on Friday? I gave him on Friday. I'm going to give him back. Pass that back. And pass that back. If you look on that, you don't have to get them out, but if you were to look on that sheet, you'll find that equation on there. And it relates delta G and K together. The nice part is you don't have to memorize it. Not even for the AP exam do you have to memorize this. It's on that paper. I just wanted to show you where it came from and what it means. Well, first off, that R is not, and this is absolutely crucial, 0.0821. Because 0.0821 is liter atmospheres per mole Kelvin. And that's why I went through the whole previous board. That I didn't make it copy down. But that R is 8.314. And it's also on your sheet. You don't have to memorize him either, but you got to use the right one. T is obviously temperature in Kelvin, and that makes sense because R, if you remember, was in per moles Kelvin, so the temperature is going to cancel out. And the ln of K is the natural log of K, of whatever K is. Now, K will be Kp if everything's a gas, and it will be Kc if they're all solutions. What if I have solids or liquids? Are there going to be any K for that? No, he's not involved in the equation if there's solids and liquids. It does not include K. Okay, so if we have all products and reactants are gases, then K is Kp. If they're all solutions, then K is Kc. And R, as I said, that's key. That's why I put it in big bold face here. You might want to put a box around it or underline it or something. R, when doing this equation, you've got to use 8.314 because I don't want liter atmospheres per mole Kelvin. They're not related to this guy, to delta G. Delta G is measured in kilojoules per mole. I want this guy in joules, not in liter atmospheres. And to get that, the reason I'm able to do that is because pressure times volume basically is joules. Okay? Does that make sense, everybody? Well, whether it does or doesn't, I guess, doesn't really matter. Okay? So, I'm going to do a couple of examples here. All right, but before I do, I want to tell you how they were related, like I kind of mentioned before. You would expect that if delta G is negative, it's a spontaneous reaction, then K is going to be greater than 1. It's going to be large. And if delta G is positive, then K is going to be very small because it's reactant favored. That should make sense. That should make sense. You know, actually, it's just saying the extreme example of what we originally said about spontaneous reactions. All right, originally it was the extreme example. I just said, hey, I didn't want to have to worry about equilibrium at that point. If delta G is negative, the reaction happens, period. You didn't know there was a reverse reaction going on. It just happens. But we only cared about it going forward. We didn't care. And, of course, if delta G is positive, it means it didn't go forward. Which, of course, now we know because the reverse reaction is so much faster. All right? Of course, there are some that go to completion. So those are your two possibilities. I have this included along with a lot of other garbage on like about 6 sheets of stuff that you should basically know for the test. And I have this included as part of it, too. All right. Now, let's do some examples. Copy this guy down. Now, of course, the nice part about this is I can determine the spontaneity of a reaction. I can determine the delta G of a reaction from the information, from the pressures from the Kp that are given in a problem. This one is actually relatively simple. I don't have to set up any kind of an ice problem. I'm told what Kp is. I'm not looking for a concentration. I'm looking for delta G. there's my one equation I need to know, right? It's right there. Delta G equals negative RT ln K. I'm solving for delta G. I don't even have to rearrange it. I just have to plug everything in correctly. So, what does delta G equal? Negative what? What's R?
8.
Right, not 0.0831, but rather 8.314 joules per mole Kelvin times my temperature. Now, 25 degrees Celsius is what? 298 Kelvin. Yeah, I got to remember that. And by the way, you may remember one of the reasons I'm using 25 degrees Celsius. Can you guys remember when we were doing the Appendix K in the back of the book? What were all those values at? 25 degrees Celsius, or 298 Kelvin. And finally, ln of K, which is 5.04 times 10 to the 17th. Now, you need to get your calculator out, because we have not used natural log yet. All right, and I want to make sure you can do it on your calculators. It's just a simple button. It should say, you know what natural log is. It's just e to the power, right? Instead of base 10, it's base e. Okay, so it's the same thing as a regular log, pretty much, except the base is different. See if you can plug that into your calculator and get an answer. There'll be one little thing you'll have to do different at the end, because that will give you delta G. But it'll give it to you in what units? Think about it. Okay, y'all get something like 1.01 times 10 to the 5th power. Is that right? Or 101, whatever, well, 009, blah, 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 right? Depending on if your calculator changes the scientific notation or not. But is that right? I don't see a lot of nodding heads. Did I do the math right?
Yeah, you're good.
1.01 times 10 to the 5th. Yeah. Sorry. Good point. That's a good reason why somebody should say negative.
That's right.
Negative. Okay. All right. So it's a negative. But the thing is, what are the units to that? Well, Kelvin cancels, right? So it comes out to be in joules per mole. All right. If you were to look it up in the back of the book for delta G, what is delta G generally in? Delta G is usually in kilojoules per mole. So basically, that guy's going to be negative 101 kilojoules per mole is going to be your answer. You see why? Because 1.01 times 10 to the 5th joules per mole would be 101 kilojoules per mole.
So we need another 0. 3 decimal places.
1, 2, 3, 4, 5.
Yeah.
101.
Take 2 by answers.
No, 1.01 times 10 to the 5th is 1.001.000, correct? And joules to kilojoules would be 101.
E divided by
1,000.
8, yeah.
That's right. That's correct. Hey, don't get me. I'm usually the one that makes the dumb math mistakes. I'm right this time, for once. That's 101. Negative. Now, by the way, since it's negative 101, what do we know? What do we write next to this? Spontaneous. Which basically just means that it's favoring the forward direction. Okay. Which we already kind of knew because K was such a large number. Look at the size of K. Huge. Right? Okay, great. Let's do 101 backwards. Try copy this guy down and we're done. So it's the last example for the chapter. Tomorrow we'll review and the test will be on Thursday. But I am going to do something different. I'll tell you about that after we do this guy. Because, as you probably know, this is going to be a long test. So I'm going to split the test up a little bit. And I'll talk to you about that after I finish this last problem. All right, so this time I need to calculate Kp. And you can see how, guys, I can go further than these. Once I have Kp, I could ask you afterwards, I'm not going to, but the AP might. After you've given you the delta G information or appendix K, hey, find KP, and then go and find the equilibrium concentrations of blah, 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 given this. Yeah, it's a pain in the neck, because this is all interrelated. It's a pain in the neck. It's like, they're all interrelated, like, families in Nescafé. It's just...
Excuse me?
It's true. Anyway. No offense to you, inbreds. Bailey. Okay, so.
Yeah, we also live on the east side.
Yeah, you're on the. Oh, that's East Escabag. I'm talking about
No.
West.
I also live in East Berwick.
Oh, okay. East Berwick, same thing.
They really
Alright.
conversation.
Okay, so look. What am I going to do for this guy? Well, it's going to be a little bit harder because I have to rearrange the equation, and I've got that natural log in there. So let's write the equation. First, though, what do I have to find? It says to use appendix K to calculate Kp. So I've got to use appendix K to solve delta G like I would have solved him a long time ago. Delta G of the reaction, do I have this on here? Delta G of the reaction equals delta G of the products minus delta G of the reactants, if you remember that. How else could I have done it? What if I gave you the delta H and the delta S? Could you have done it that way? Absolutely. Delta H minus T delta S. Guys, I know, but guess what? The AP exam has all of it on there. Products minus reactants. Okay? So if you use delta H minus T delta S, you could do it that way. We use delta G, it's a little bit quicker because I'm just going to have, well, remember all the mistakes we were making back then. Am I going to look this guy up first? By the way, if you have I don't need you to open it up right now, but I will look at the right columns. Remember all the mistakes you made. Would I look this guy up first? No, I look these guys up. Products minus reactants would be 2 times N2 gas. Now look at, again, I'm going to use this as an example of how you don't always have to look stuff up. What's the delta G of N2 gas going to be? Exactly. It's going to be 0. What's the delta G of O2 gas going to be? 0. So that's nice. Minus, now that guy ain't going to be 0. 2 times N2Os. I have it looked up. You don't have to get it. It is 104.2 kilojoules per mole. All right. And that, again, I have the math for that done as well. Negative 208.4 kilojoules per mole. Now, what is that? Again, I'm going to use that other equation. Remember, my R is in joules, correct? So I got to convert him to joules. That will be 208,400 joules per mole. I know it's a big number, but you could use scientific notation if you want to. 2.084 times 10 to the 5th. But either way, that's what delta G is. Now, if I know what that's what delta G is, I'm looking for K. Looking for K in all the wrong places. All right, so delta G is going to equal negative RT ln K. Can we rearrange that? Yeah, the ln K is going to equal what? Delta G over negative RT. Does everybody go with that? Okay. So let's plug my numbers in, and then we'll have to take the inverse natural log of this. Okay, so delta G is 208. By the way, was he positive or negative? He was negative, wasn't he? Negative 208,400 joules per mole over negative 8.314 joules per mole Kelvin times, again, if I'm in appendix K, notice this problem never said what the temperature was. If I'm using appendix K values, what must the temperature be? 298 Kelvin. Okay? And therefore, you get, well, you get 84.1 up here. So this I do want you to do. I think everybody can do that much math. What I want to make sure you know how to do is, if I have ln K equals 84.1, what do I have to do? Take the inverse natural log of ln K, which of course is K, and the inverse natural log of 84.1, which is what? Make sure you can do that on your calculator correctly. It's a big number. I believe it's 3.3 something.
That's a huge number. Yeah, it's 3.34.
Times not to the.
No, I know. Times 10 to the 36.
Okay. All right, so if that's what K is, does that make sense? Well, let's take a look. Look here. Was delta G spontaneous? Yeah, it was highly spontaneous.
Any 9, 10, or 11
Would I expect to get a K that's greater than 1? Yeah, much greater. Okay? And that's what you do get. All right, now here's what we're going to do. I'm going to shut this off now, and I'm going to talk to you about the test. Oh, your homework. I guess I should tell you the homework first, too.
It's okay if you know.
It's not okay. Well, I don't need that on the camera. I'll figure it out.